that's working. Students will be able to use the first and second derivative test to find extrema, so we're going to do a second day on 4.3. And the first two are, I don't know, they're not just polynomials, they're a little tougher. But let's talk about the domain. And when we look at minimums and maximums, there are certain places where we can have minimums and maximums, certain places that appear to be a min or max but can't be. So my question is on number 4 to start out with, what can x not be? 0, right? Doesn't matter where the 1 over x is, it's in the power of e, but that means that x cannot be 0. So we'll just write it like this for now. X cannot be 0. What's happening at 0 when this makes a denominator 0? What's happening there? Vertical asymptote, and it doesn't really matter that it's in the power. That's kind of the cool part. So we'll make a note that there's a vertical asymptote at x equals 0. So now let me ask you one more question before we start actually doing the problem. Can I have a minimum or a maximum where there's a vertical asymptote? No, the function doesn't exist there. It doesn't make sense to have a min or a max there. But our math would suggest that there is, but you have to know that there isn't. All right, now what do I mean by that? Let's take the derivative. First times the derivative of the second. And I have to multiply that times the derivative of x to the negative 1. So times negative 1 over x squared is the derivative of 1 over x. So first times the derivative of second plus the second times the derivative of the first, which is 1. Whoa, what can we take? We can take out an e to the 1 over x. And then that's times negative 1 over x plus 1. Because one of the x's are going to cancel, and it's negative. Now we're going to set that equal to 0. So we want to know where negative 1 over x plus 1 is equal to 0. Because e to a power cannot be 0. That's impossible. So negative 1 over x is equal to negative 1. So cross multiply, x is equal to 1. Oh, and one other. I was like, where am I going to get 0? This is the derivative. So we also want to know, we also have x equals 0 also. Because that's where the derivative would be undefined. Not only here, but here also. So we're going to throw these on a number line. 0 and 1. And we're going to plug in negative 1, how about 1/2, and how about 2? Now we're going to plug those into the derivative. But you cannot make e negative. So I'm not really, as far as getting positives or negatives, I'm not even really going to consider e to the 1 over x. It can't be negative. So if I plug a negative in there, we have negative, negative 1. 1 plus 1 is 2, so positive. So this function is increasing to 0. Then if I plug 1/2 in there, 1 over 1/2 is 2, so negative 2 plus 1 is negative 1. So this function decreases after 0. If I plug 2 in, negative 1/2 plus 1 is a positive 1/2. So is there a minimum or a maximum at 0? No? Remember what we talked about? If you don't consider what's happening at 0, you're going to say it's a local maximum, right? That's what I would say if I didn't consider it. But what's happening at 0? A vertical asymptote. So there is not a maximum happening there. There is a local minimum at x equals 1. If you never consider the domain, that looks like a maximum to me. I would say, yeah, absolutely maximum, but there's a vertical asymptote there. All right, so we have to consider the domain if it's not just a nice polynomial. On number 6, I picked this one because piecewise gets a little tricky. I know that, we could do this first. Y prime is equal to, and we could take the derivative. So negative 2x and 2x. Those are the derivatives for x less than 0 and for x greater than 0. We can only put equal there is if we know both of the slopes at that point are 0. We probably could, but we usually don't put an equal on one of those, not for derivative. For the function value, yes, but not for the derivative. The critical values is where the derivative is 0, where we can have local minimums and local maximums, but the critical points for both of those happen to be 0. Well, this is the point 0,3, this is the point 0,1. So this is not a continuous function. Now that doesn't mean we don't have minimums and maximums, we still can. But now we're going to have to kind of appeal to our knowledge of the graphs. On the top one we have 0, 3, 1, 2, 3, but that's an open dot. And it looks like this on the left side of 0, roughly. Here is 0, 1, closed dot, and it's a parabola that's going up because A is positive. So what do you think? Is there a minimum or a maximum or none? What's happening there? No local maximum, right? Because that'll increase to that point forever. But there is a local minimum value there because remember there's no value here. That's the only value we have at 0. So there is a local minimum at x equals 0. And we could say local minimum of 1 at x equals 0. We could even tell pretty easily what that point is. Local extreme values of the function. Oh, they actually want values. So if I go back to this one and I plug 1 in, it's a local minimum of e. And if I was to answer what they want, that's the actual value. That's the value. So I wouldn't put that. I wouldn't count it wrong if you said where it's at, though. If I follow, if we're following the instructions. All right, couple tricky ones. Number 8's a little more straightforward in what they're asking. Use the concavity test to determine the intervals on which the graph of the function is concave up and concave down. So let's get the first derivative. Plus 12x squared minus 4. Second derivative is negative 12x squared plus 24x. And we're going to set the second derivative. And notice I'm not really considering the domain because this is a polynomial. Nothing strange happens with polynomials. I can take out a negative 12x, which is x minus 2. So x equals 0 and x equals 2 are really possible points of inflection. Not necessarily, but it's possible. But that's where concavity changes, is where the second derivative is 0. So 0 and 2. Let's test negative 1, 1, and 3. So negative 1, I just need to know that that's 12 times negative 2, that's negative. So concave down. Negative 12 times negative 1, that's positive. Concave up. And then 3 is negative 36 times a positive 1, that is negative. So A, what do they want? Concave up? Concave up on 0 to 2. Now I know it doesn't say justify, but our DCA does. It asks us to justify. So how would you say that you know it's concave up there? It's pretty simple. It's not complicated. Yeah, second derivative is positive. So we say second derivative is greater than 0. It's a very simple statement, but it's worth a point on the DCA. So don't have that be the reason you have to retake it. It's a very simple statement. B, concave down on negative infinity to 0 and 2 to 3. And if we were to ask to justify it, it'd be second derivative is less than 0. And I know the instructions don't ask you that. Not 2 to 3. 2 to infinity. There we go. Number 12, very simple. But I'll make it a little longer than I should. Second derivative is e to the x. They're all e to the x, right? So if we plug anything into e to the x, is it going to be positive or negative? Positive, right? So concave up on 0 to 2 pi. As a matter of fact, can you draw the graph of e to the x? Do you know what it looks like if I asked you to do that? Yeah, yep. So it's always concave up. There we go. So you could either think about the graph on that one, or you could do the calculus either way. Do the second derivative. Always concave up, never changes. Find all points of inflection of the function. All right, take a deep breath, stretch out a little bit. This is a long one. This is going to take a while. This is a doozy here. We got to get the second derivative of number 14. I love this one. Here we go. Really makes you think. Can you get the first derivative? Let's try that. I don't want to ruin all of it for you. You should have some fun. Oh, don't move anything to the bottom because we have to take the second derivative. So just get that first derivative line and stop. Don't move anything to the bottom. Okay, oh, I don't want you to go too far with this because we have to do the second derivative. So first times the derivative of the second. Plus the second times the derivative of the first. Now we do want to simplify this a little bit, but I don't want to move that down to the denominator yet. Those cancel. Do we have negative x squared times 9 minus x squared to the negative 1/2 plus, oh, and I should write it like this, 9 minus x squared to the 1/2. Agree with that? Everybody good on that one? All right. Oh boy, now we got to do the second derivative. That'll be fun. First times the derivative of the second. Negative 1/2, 9 minus x squared to the negative 3/2 and times negative 2x. There's first times the derivative of the second plus the second times the derivative of the first. So negative 2x, second times the derivative of the first. So I just have to write this again. But then we haven't taken the derivative of that yet either. So 1/2, 9 minus x squared to the negative 1/2 times negative 2x. Woo, Nelly. Now let's start moving stuff to the denominator. The 2's cancel. Negative, negative, negative is a negative. So I'm looking at negative x to the third over the square root of 9 minus x squared. Not square root, excuse me. I don't want to do that yet. My apologies. I want to keep it as a power. 9 minus x squared to the 3/2. Minus 2x over 9 minus x squared to the 1/2. And also, let's see, minus x over 9 minus x squared to the 1/2. Now, two of these denominators are exactly the same. So minus, we could go, what should we do? If we go minus 2x, is it going to be plus x over 9 minus x squared to the 1/2, right? Because we'd run the negative through, then they'd both be negative. Everybody catch that? And there's, no? Yeah, aren't those both negative? So if I put a negative here, that one has to be positive. Yeah, okay. All right, kind of the last step where we want to combine these now. So I have to multiply this by 9 minus x squared to the 2/2, which is 1, by the way. So that's negative x to the third. Now shouldn't, oh, that's 3x. Oh, that's, duh, duh. You're like, how come he's not combining those? Hey, zip it. There we go. Now I don't have to FOIL, you can just distribute. Now keep in mind that's to the first power. So what do we have? Minus 27x plus 3x to the third. All over, and now we finally have a common denominator. This is 2x to the third minus 27x over 9 minus x squared to the 3/2. Now I want to know where what are we doing? Second derivative, find all points of inflection. I want to know where the second derivative is 0 and undefined. So x, well, we can factor an x out. We get x squared, 2x squared minus 27. It's rather, considering where we were, it's not really, it's pretty compact, ended up being compact. So x is equal to 0. 2x squared minus 27 is equal to 0. So x squared is equal to 27 over 2. So x is plus or minus square root of 27 over 2. Well, let's talk about where it's undefined. So actually we should say it's defined from -3 to 3, right? Inside there. Because if it's 9, you're going to get 0 in the denominator. And we can get 9 by -3 and 3. So it's defined in between there. The derivative is. But if we look at the original, can we have 3 and -3? Is that okay? Or is it not okay? What about the original? Are we okay? Can you take the square root of 0? Yeah, no problem. So even though we could not include it in the derivative, it is a point on the original function. All right, so we have endpoints here. But here's kind of something strange about this one. If you take the square root of 27 divided by 2, you get some extraneous answers. So we can't use these 1 because it's outside of the domain anyway. So the only possible point of inflection is at 0. So now if we go -3, 0, and 3, we're really only checking 0, so we can test -1 and 1. So if we put -1 into the second derivative, where would be a nice place? Right here. Negative times a negative is a positive, so concave up. If I plug 1 in here, we get 1 times a negative, which is a negative. So yeah, point of inflection at x equals 0. Isn't that a fun one? I mean, as in not fun. If I meant not fun, it's fun. Woo! Look at that. Isn't that beautiful? That's awesome. Okay, let's keep rolling. Even though we're exhausted now. 4x to the third minus x to the fourth. Do we have white space or did I kill all your room? You got some above it? Go above it. Yeah, there's some room above. This one's not very long. Yeah, right above it. Looks like everybody has, looks like number 6 was fairly short if you wrote fairly small. First derivative is 12x squared minus 4x to the third. Now this is a nice polynomial, so we don't have really anything crazy going on here. 24x minus 12x squared. So we want to factor 12x out. We get 2 minus x. So x equals 0, x equals 2. You'll learn to appreciate polynomials. They're very nice. 0 and 2. Let's test -1, 1, and 3. So -1 into the second derivative. -12 times a positive looks like concave down. 1 is positive, positive, positive. 3 is positive and negative, negative. So point of inflection at x equals 0 and x equals 2. Now on the DCA, we are going to be asked to justify this. And all we have to do is say second derivative changes signs. Or changes sign. Changes sign or changes signs? What do you guys think? Changes sign? Probably just sign. Sign? It don't matter. I'll give you credit either way. I'm not an English teacher. Yeah, it doesn't matter how it changes signs. It just has to. I don't know. You all good? All right. How about the second derivative test to find local extrema for the function? Now, if you are asked to find the local extrema, you can do any method you want. So this is an option. Rather than doing a number line, didn't we do first derivative test? And we did number line for this and found out that ended up that not being a minimum or maximum, but this is a minimum. You could do number line on the first derivative. But if it's fairly easy to do the second derivative, you can do the second derivative test. Here we go. So y prime is equal to 15x to the fourth minus 75x squared plus 60. We can set that equal to 0, but we can factor out a 15. X to the fourth minus 5x squared plus 4. X minus 4, x minus 1, x squared minus 4, x squared minus 1. So x is equal to plus or minus 2, x is equal to plus or minus 1. And we could certainly throw those on a number line and decide our minimums and maximums. But we're asked to use the second derivative test. So we'll do second derivative. 60x to the third minus 150x. And now I just have to evaluate the second derivative at all of these points. So for x equals, let's go negative 1. Actually, we'll go negative 2, negative 1, 1, and 2. And we're talking about the second derivative here. Negative 8, isn't that negative 480 plus, what's that going to be, 300? So negative. Concave, it's concave down there. Well, if this is what makes the first derivative 0, that means it's a potential min or max. And if it's concave down there, then it must be a local maximum. So I know I have a local max at negative 2 for sure. If I plug negative 1 in, we get negative 60 plus 150, that's positive. So now we have a local minimum, because if it's concave up, then the graph looks like that right there. So local minimum at x equals negative 1. 1 in here is 60 minus 150, that's something negative. That makes it concave down, that's a local max. And I got x equals. And x equals 1. Plug 2 in here, that's going to be the 480, but then minus 300. That'll be positive, and we have a local, let's see, concave up. That's a local minimum, and x equals 2. So there's your second derivative test. If the value makes the first derivative 0, exists on the function, and this is just a polynomial, so it does, and it's concave up there, it must be a local minimum. We really never did a number line, we just plugged values in. Sometimes that's easier than making a number line. Now, when you're asked to do that, I'll need to see the work. If you're not asked a specific technique, then you can choose. All right, 35. Y prime is equal to first times the derivative of second plus second times the derivative of the first. We can factor out an e to the x. Now, the reason they have an e to the x is not all functions can be 0. It's not possible. You can't make e to the x 0. So the only possibility is negative 1. Now we could very easily throw that on a number line. I'd probably use number line for this one because it's only one value. But we are asked to do the second derivative test. First times derivative of second plus second times derivative of the first, and then plus that extra e to the x. So we can take an e to the x out and we get x plus 2. Now we're just going to plug negative 1 into the second derivative, and that ends up being positive. So concave up, so local minimum at x equals negative 1. There's the second derivative test for maximums and minimums. I don't know. I don't know which is easier. If you're asking, geez, well, which should I use? I don't know. Sometimes the number line's easier. Sometimes second derivative is easier. I'd probably use a number line on that one. Wouldn't have to do the second derivative. All right, what do we got here? Use the derivative of the function y equals fx to find the points at which f has a local maximum, local minimum, or point of inflection. What I don't like about this question, it says find the points. I think what it really means is find the x values, because we would have to know the original function to be able to get the points, the x and the y. So we're just looking for x's here. So the local maximum, local minimums. Now this is a nice polynomial, so we only have minimums and maximums, and we only have points of inflections. We don't have anything crazy. We don't have horizontal asymptotes or jump discontinuities. That's why they're saying, well, we can find these three for this one. So the possibilities are 1, 2, and 4. So we're going to put these on a number line. I'm certainly not taking the second derivative of that. 1, 2, and 4. Let's plug in 0. How about 1.5, 3, and 5? And we're going to plug that into the second derivative, but here's what's nice about that is I don't really have to consider this one because it's squared. So it's not going to determine whether we have a negative or a positive. I'm not going to pay attention to that one. So if I plug 0 in, I got a negative times a negative. That's a positive. The function's increasing. 1.5, that'll be a negative times a negative. Oh, it's still increasing. So what must have happened right here? Not a minimum, not a maximum. It's only one other choice, right? That had to be a point of inflection there. 3 in here is a positive times a negative. Now we have a local maximum. And when we plug 5 in, positive, positive is positive. We got a local minimum. So A, local maximum at x equals 2. B, a local minimum at x equals 4. And the point of inflection happened at x equals 1. And again, I know it's a point of inflection because it's a polynomial. It's not some crazy function that we have to worry about. Can't really find points like they say, so it's not worded very well. They mean x values. Everybody good? Oh, we get to graph a little bit. Connecting f and f prime. Sketch a smooth curve y equals f of x through the origin. Oh, through the origin. They gave us a point to go through. Right there. That kind of locks it down. With the properties, and it's very vague. We can have lots of different versions of this, but it says that the second derivative is less than 0 for x is less than 0, and the second derivative is positive for x greater than 0. So let's talk about to the left of 0. What do they want our graph to be to the left of 0, if they say that? Concave down, that's right, concave down. That's it, concave down, that's all they want, just that. So how about this? That looks concave down to me. And well, I said there could be lots of versions of this. Well, if to fit their criteria, I could have drawn it like this. I could have drawn it like this. All I need is concave down. That's it. That's all they're telling me, just concave down. All right, what about this over here? To the right of 0, concave up. So it just has to switch. So it could be this one. It could be the original one. Yeah, that would be weird. We don't want it to have we don't want a cusp or a corner there. So just make it smooth. Like that would be a nice one. And it even said make it smooth, which means no cusp and no corners. Lots of different versions of that. They would all look similar though. All right, let's ramp it up a little bit. How about this little chart? Much easier than it looks. It looks like, oh my God, I gotta do all that. I'm gonna make it as simple as I can for you. The first thing I always do is I plot the points. They have 1, 2, 3 points. And a fourth grader could plot the points. That's as easy as it gets, right? 2, 1. 4, 4. 3, 4. 2, 3, 4. 6, 7. 5, 6. 1, 2, 3, 4. 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right. Now here's where a fourth grader might have a problem. getting all this information in here? Well, for less than 2, what do you think it means by falling? Decreasing, right? Decreasing, but in a concave up manner. Can you draw that? What would that look like? To the left of 2, falling, but concave up. And it'd be, all of yours are going to be slightly different, but here's what it should look like. Concave up and falling. Boom, like that. Just make sure it looks concave up, just don't draw a straight line. Have a little curve to it, and decreasing. From our 2 to 4, now it's going to go up and concave, still concave up. So up and concave up, like that. Then from 4 to 6, so we got this part, we got that part. From 4 to 6, rising concave down. Rising concave down, like that. Something like that. Check, got it. Falling concave down after 6. Falling concave down. Now they gave us some extra information. They said at 2-1 we have a horizontal tangent. Yeah, that's a minimum. And at 4-4 we have an inflection point. Yeah, it went from concave up to concave down. And then lastly it says horizontal tangent here. But I'll tell you what, I didn't need this, I didn't need this, I didn't need this to graph it. It was nice. I mean, okay. Yeah, it makes sense, but I didn't need that to graph it. Not really. Questions? All right, try the last one. Oh, I got to make sure. Yeah, we got time. 26. Yeah, plenty of time. You can at least plot the points, right? Zero, 2. 1, 0. 2, -1. All right, I got that. F prime doesn't exist. It's 0. It doesn't exist. These 2 lines, I can investigate that later. That doesn't really help me a lot. Not to graph it anyway. It makes sense after you graph it. This is what I want. I want this, really. And this is nice, but I want those 2 lines. If f prime is negative, what does that mean as far as the graph is concerned? And okay, slopes are negative, but it means the graph is decreasing. That's really what I want to hear, decreasing. And you're right, slopes are negative. That's exactly right. But if the slopes are negative, the graph is definitely decreasing. And what does this plus mean for the second derivative? Concave up. So decreasing concave up from 0 to 1. Decreasing concave up. So it's got a curve like that. What does this negative mean? Decreasing concave down. Oh, and this says that the graph is above the x-axis. This says the graph is below the x-axis. So above and below. Decreasing concave down. Decreasing concave down like that. And then increasing concave down. Increasing concave down. So now we kind of get a choice. Oh, but it says that the values are all negative. So let's do something like this right here. But it says f is an even function continuous on -3 and satisfies the following. I don't care about the instructions. I just want us to graph it. I don't know where A through C is actually. but we graphed it from 0 to 3. How are we going to get the other side? Because they really want us to graph this from negative 3 to 3. What are we going to do? Flip it. Yeah, what does that even mean? It's the same thing.
A negative gives you a positive.
So
Negative
it,
3 would give you 3.
yeah, uh-huh.
3 would give you 3.
Right.
Flip it over the y-axis.
It's a reflection over the y-axis, right? Yeah, yeah. It's symmetric over the y-axis. There we go. 1, 2, 3. So like down like this, down like that, and something like that right there. Now we have it graphed from negative 3 to 3. It's not that hard. You just got to take it one little piece at a time. I always plot the points first, and then what's it doing in between those. That's really, this is just f prime does not exist at 0. Yeah, what's happening here? Why doesn't the first derivative exist there? It's a cusp, right? So if the first derivative doesn't exist there, then the second derivative can't exist there. That's not possible. And then over here at 2, we have another cusp there. So that's why it's saying does not exist. Quite frankly, yeah, this makes perfect sense after you graph it, but it doesn't help me graph it hardly at all. I don't really use that. All right. I mean, I suppose saying it doesn't exist means there's like a cusp there or a vertical asymptote there, or something weird's happening there. I suppose it could help you.